All right, so next class is our test, which covers our second chunk of the class, which started from, well, let's see, we left off at the first test. Our first test focused on looking at rate of change functions and determining what was accomplished due to them. And we broke it down kind of piece by piece, saying, okay, so I can approximate constant rates of change if I look at small moments. And through the first test, we got up to the point where we could express in open form a messy summation that would approximate accumulation over any interval we wanted, including we could even do a total accumulation by starting from a starting value, starting from an initial value plus what happens due to the rate function. So right after the first test is when we introduce integral notation. So that's where the second test picks up right from there. If you want to kind of look at what we were doing back then, this was the tail end of September, beginning of October. So whatever that makes, about 6 weeks ago. And we started looking at how to use integral notation to express, even though we didn't do too much with it at the time, how to express exact accumulation by imagining not just small intervals of width delta x, but infinitesimally small intervals, and we look at all the different values of a rate function over a given interval, starting from A to B or from A through mystery x, make it a function so we can express accumulation both a set amount during a closed interval, or we can express accumulation in general exactly using integral notation. And again, we can talk about just the net accumulation starting from 0 and moving up or down from there. Or we can also institute an initial value and then express total accumulation. So that's where we started out. But then right after that, we took a break and did a whole bunch of derivative rules. So as I said before, the test isn't going to be about your derivative rules. There aren't questions on this test that's find the derivative of, find the derivative of. We did that on our mastery test. But there are bits and pieces kind of built in and around when we were talking about derivative rules, about what derivatives are for, or how I want to find rate of change, how I can visualize it based on graphs, match up accumulation and rate graph features that indicate specific key points in the development of whatever quantity it is, whether it stops accumulating and starts dissipating, or whether I've got a maximum or a minimum, whether I've got something that's increasing and increasing more and more quickly, or it changes from increasing to decreasing through an inflection point, those sorts of things we looked at, just the visuals of that beyond the computations. And also, we talked about how we can kind of go back and forth between integral notation expressing accumulation and the associated rates of change. And we're going to talk a little bit more about that today, just kind of things that we've already talked about in passing, with kind of a preview for what we're headed to after your next test. But with our derivatives, once we got good at them, we did some more advanced derivative types, including implicit differentiation. And I know you have a quiz that involves a little bit of implicit differentiation and related rates that's yet due tomorrow night. That's in Math AS, or iMath, whatever it's called, yeah, iMath AS, just like the previous one was, so that you can do the computation and list all the formulas in whatever form, and it'll recognize whatever form you enter as equivalent. So make sure you remember that's due tomorrow night. There is a review session tonight in the Palo Verde Tutoring Center from 3 to 5. Did I say the right tree name? From 3 to 5 tonight. Or 3 to 5? Yeah, so right after class, essentially. But let's see. I think I have that in here. That's a review. Oh, no, I put in an announcement. Sorry. I was thinking it was in the last week's stuff that we're doing. But in terms of stuff that we're doing, I listed some things in this week. So there's a written quiz. I put this up a couple days ago, I think. There's a written quiz in iMath AS that's due, as I said, it's due Wednesday night, tomorrow night. There's an optional set of 40, 45 questions or so in Canvas that are kind of an overview in order through the semester, what we've talked about since your last test. So it starts from that moving picture of how we got from rate to accumulation, but then builds from that. So it's remembering the parts of that sum. The pieces of the sum aren't going to be tested on your test number 2, but just the meanings of the details of the integral sign, things like that, moving onward from that. The end part of it, the exact part is. So that practice that's in Canvas, those 40, 45 questions, you can do them. It will tell you if you're right or wrong. It doesn't count in your grade. It's just extra questions, kind of an assortment from the last 6 weeks or so to help you remember a variety of things, questions that you didn't just do in iMath. On Thursday, last time at the end of class, it was kind of hectic with lots of people need to show their IDs and that. So we're going to do it kind of like we did at the mastery test instead. So on Thursday, I'll be here earlier than usual. I'm going to be up at that door there to check IDs. Barb and or Axel will be here as well to check IDs, get you in, get you a Scantron so you can come on down here, sit down, start bubbling things in while we're checking everybody's IDs. And then as soon as the line is dissipated at the door, we'll start passing out tests. And as soon as everyone's seated and has a test, then we'll start our 50 minutes. But make sure you're here on time. You don't get extra time once the 50 minutes is started. It starts at the same time for everyone. So you just get that 50 minutes, and then I'll pick up the remaining tests at the end. So that's what that last part is about on Thursday. Let's see, there's something else online I wanted to point out before I do anything else. Just look at the Canvas questions that I was mentioning. So in terms of review, look over what we did, all these week-by-week lists of things to read, some examples that I pointed out there. Look at the lecture videos that are on YouTube if you want to review specific ones. I tried to put in topics so you can see what they were, not just like the title of the day or a book section number. But all of these things here, this reverse process handout, that was the explanation of how we put together the derivatives. So this was the explanation of finding intervals and doing the slope computation and how we realized that the x plus delta x and left of x and all that stuff made it a little bit tedious. So we came up with a second process instead that had that sliding tangent line and a h that always slid a fixed interval in front of the current value of x. So that's what that reverse process handout was about that we went through together in class. List of derivative rules. Make sure you know them. There aren't going to be any super crazy things like we're on your mastery test, but don't forget how to do the derivative of sine functions or square root functions or things like that have shown up a lot in our applications. Some reflection things to think about as you're studying. These aren't specific topic-wise. These are things to think about, like trying to get you to think about the big picture instead of how do I solve an individual type of problem. How to conceptualize or put together some of the main ideas and just tips on how to think about studying, apart from just the practice and problems aspect of it. Here's a list of a bunch of topics, which, I'll just open it up this way. I think I showed this before, but starting from integrals, understanding where the integral, like how the integral notation functions, what the different pieces are, what is and isn't allowed in various spots, what it means, and the process from going from rate to accumulation in general, even though we're really only focused on the end part, the integral part as a part of this test, it came from someplace, so just the way math is always cumulative, you still have to remember some of the stuff from prior. Developing our derivative function, a bunch of different expressions there, some things to think about. All of your derivative rules, know your derivative rules, as I said. Implicit differentiation and related rates. Those are interrelated because whenever you're doing a related rates problem, you're taking a derivative with respect to not thinking of every symbol in front of you as a basic variable. Each of the functions, each of the letters in the functions that you've written are functions themselves. Like the thing that we had about was a snowball melting or something, we had a volume and a radius, and the volume and the radius both change over time. So in essence, they are, even if we're writing just v and r, they're both functions of time, as opposed to being just simple variables, and we're taking derivatives with respect to time in those related rates problems. And then, so these aren't necessarily in order. We did this coordinating the accumulation and the first and second derivatives. We did that earlier on, but that was the looking at all the graphs and thinking, oh, so if the derivative is positive and increasing, that must mean that the accumulation is growing. The amount of whatever I have is growing, and it's growing more and more quickly. Or some, those sorts of things. Figuring out what various points on a graph mean. There's several questions about that in the Canvas quiz as well. So speaking of Canvas, well, it's Canvas, I don't know what I'd call it, review question set. but it is this practice problems. It's not for credit. It says 100 points there because in order for us to put it in there for you to do, we have to assign points to them, but they don't go into any part of your grade. It's just you can see how many points you got out of 100. And the questions, you can see them all at once. It's not like a mystery test and you only have one chance and that's the end of it. These are just, sorry, this is the teacher view of it. And there we go. So there's some with videos in there to look at moving parts and see how they're related. But there's a variety of different sorts of questions, including some of these that we haven't talked about in a while, writing integral expressions to model accumulation. So I do want to talk a little bit about that because it's been a little while since we talked about that aspect of it and just how rates of change. We've been dealing with taking all the derivatives and doing a lot of algebra. How the rates of change relate to accumulation and how accumulation can be tied back to rates of change. So, I believe I have this here. There we go. Where are we? Sorry. Yeah. I'll just kind of, oh wait, this is not what I wanted. This one's the one I wanted. There we go. All right, so just kind of recap a little bit, and then we'll get back to our notation and review here. So in the first half of the course, we looked at the situation where we knew how fast something was changing, our rate, and we wanted to know how much of it we had. So our process was that we would initially go through several steps to get to this idea of an exact accumulation, which was to find and use a few rates every so often from this rate function that's continuous and has infinitely many values over any interval, but just use a few discrete points on the graph and use each of the rate values for a small moment at a time. And then using constant rate of change, MDX, doing that multiplication, we can get an amount of accumulation during each interval. And we sum up all of those, and we get an approximation. And if we make the intervals really small, it's not too bad of an approximation, although there's a lot more things to add. But see if you can do this. So using the exact rate of change function, R, on the left here it says we've got a rate of change of elevation as a function of distance from the coast. So this is the rate, not in like miles per hour sort of rate, but in 100 feet per mile. So this starts at a rate of 3, meaning 300 feet per mile, right at the coast. By the time I'm a mile in from the coast, it's a little bit lower than that. By the time I'm 2.5 miles in from the coast, the elevation is increasing still, but it's only at a rate of less than 100 feet per mile. And then it begins to increase this elevation increase again. So this is a picture of the elevation as they go from the coast inland. So see if you can write an open form expression for not this, the actual elevation, but for F, the net change in elevation. I just needed F to call it something. The net change in elevation from at the coast to someplace, let's see, net change in elevation starting from A miles to X miles from the border. So we won't start at the coast, we'll start at A miles from the coast and go to X miles from the coast. Sorry, I wrote border here. Kind of changed my mind here. Could have been from the border of some state too, but this is the coast. So pretend where that cursor is, it says coast instead. So looking for net change in elevation starting at A miles in from the coast up through any point that's X miles in from the coast. On some road in a straight line going away from it, you can imagine. writing thing going here. Why is this doing that? It won't stop. I'm going to try this again. All right, so if I want to write an expression, and I want to kill this tablet or something, but. So if I want to write an expression, a function f, I guess I won't. I will just go with what's there. Close this thing because it's being difficult. If I want to write a function f, starting at a miles through x miles from the border, it doesn't actually say this, but we're using x here as a variable as opposed to using a as a parameter. So a is one specific location, and we're going to let this x miles from the border vary as we go inward. So if I want to express the accumulation due to this rate, the name of the rate function is r, and I could call it r of x if I were talking about that function there. If I want to write an open form function f to explain what it is, I don't have a formula for r, so I'm just going to write an expression that represents accumulation due to rate, capital R. I'm going to need to do something like this. So rate r, you can see here I've got r of t. This would be a rate function, and t here isn't something that I see up in these graphs. Like I didn't pick, t is this, we called it a dummy variable. It's just a placeholder right now. I'm going to let t take on all the values from a through x. So you could use whatever letter you wanted, just not a or x or r or something else that's already used. So typically we use t unless t was used someplace else, but I evaluate this rate function at every point between a and x, multiply it by a small, infinitesimally small amount of change in the independent variable. So I let t vary by a tiny bit and multiply r of t, the rate at any value between a and x, by that variation by a small bit to get a tiny bit of accumulation. Then we sum up all of those little bits of accumulation that happen between x equal to a and a general value of x. So x then appears on our final function, t does not. That's why f here is a function of x. So how is f related to, it said that pink graph on the right is labeled as e, the actual elevation. What's f if it's not the actual elevation of the road? Yeah, it's the net change. It's the net change since a miles inward. So if I wanted to make a function that was the actual elevation at any point x miles from the coast, I would need to know, let's see, well, some elevation someplace. I'd need to know either, like, this seems to be, if this is 0 miles from the coast and it's an elevation of 300, that sounds like there's a cliff at the coast. And then it goes upward from there. But I'd have to have some sort of value. It doesn't have to be at x equals 0. It could be at some point. But if I wanted to express elevation in general, as long as I have some distance and the elevation at that distance, then I can use this rate to go either forward or even backwards closer to the coast from there, so that I have actual elevations instead of just net changes in elevation. So this expresses net change in elevation starting at this point A, wherever A miles from the coast is. This thing is just difficult today. Get it out of the way. A miles from the coast, and to whatever happens, X miles inward from the coast. And so if X were the same as A, this would be 0. And that doesn't mean that the elevation at position A is 0. It just means if you haven't gone anywhere, you haven't gained any elevation. So this open form here, it's just the reason that we write this is two reasons. One, you can explain what's going on. Say, I'm going to take this rate function, I'm going to integrate it, I'm going to let all the accumulation happen. Use the rate from A to X. Second reason we use it for something like this, where we don't actually know a formula for function R. We can at least write it like this for now, and if we had a function for this elevation rate of change later, we could plug it in there and then get a closed form from this, because we have the tools to get a lot of closed forms from this already, because if we can see a rate of change function, in a lot of cases we can figure out, because of familiarity with derivative rules, what did this rate function come from. Not everything is possible to think backwards like that about, but many things are. But this accumulation, it's the sum of many small bits of change taken over at various rates, all added together. So we have this net change starting at a specific spot and going to either a specific second endpoint or to just in general this value of x like we did here. So it's the sum of many bits, each this m dx, dy equals m dx, all those things we learned at the very beginning. This is our m dx part. Put them together, we get a net accumulation. So to write f in terms of E or E in terms of F, these are two related things. The only difference between those is knowing one specific value that I can tie down, so I can relate that here. So if I have this E, and it looks like here that E of 0 is 300, my elevation at position 0 is 300, I could figure out how E could be written in terms of F, or how F could be written in terms of E, either one. You can solve for either variable just as easily, either function name, I should say. But also, this method here, E, if that represents the actual elevation, E of something is the actual elevation at something miles from the coast. So E of x is the elevation at x miles from the coast. E of A is the elevation at a miles from the coast. Then this would certainly tell me the net change between position A and position x, just subtracting, if I knew function E. Then I could find this expression that way. But I could also say that just rearranging this, thinking about how to write this. If I wanted to write, oh, E of x, that's just the whatever some starting elevation plus whatever happens due to my rate. That's just this exact same expression rearranged. E of x equals E of a plus this integral. Or E of x equals E of anything plus an integral that starts at anything, doesn't have to be a, just any position that we know an input-output pair for. So this net change we can express this way, maybe obviously, but that's the same as this. And we can also express E of x by moving this E of a across the equal sign, just rearranging it and saying, oh, I have an expression for total elevation or actual elevation as opposed to just net change in elevation. So the net change you can find by doing final minus initial. We talked about that like the second day of class, maybe even the first day of class. Dy equals y final minus y initial, or I think it was Z's I was using at the time just to be generic about it with memory on your phone. Final minus initial gives you change, net change. But you can also find that by writing an integral, integrating a rate function, if that's something that you know, taking a rate of change function and integrating that rate times a change in the independent variable, or MDX sort of expression, between 2 points, whether they're at a beginning point and an end point, two specific numerical values, or even like this, parameter values, parameter symbols. Or I could write it as, like we had on the last slide, through a generic x so that it's a function. And those two are equal, whether I have, like I said, I have to have one starting value. I'm not going to have two different x's or an x and a y or something like that in those two spots. But thinking of a and b previously as parameters, a still as a parameter, but x as a variable or independent variable of this function, all of this expresses that net change. So you can think of this a, you'll see this described someplace as a reset value, or just it's the relative point of beginning. Lots of functions you learn have this some sort of initial value in them, whether it's exponential growth. Initially, the bird population was 2,000 and was increasing by 1% per year. Well, 2,000 initially, initial relative to what? Well, let's say initially we meant 1995. Okay, so then this is like in 1995, A equals 1995, we'll call that times 0. The bird population was f of A equals 2,000. So you can have those sort of defined starting points, and you can assign them to be times 0, or you can assign them to be whatever you want. Like 1995, let me just use 5 for that. Whatever you want to do. It's up to you when you're writing your own things. But this is kind of the reset, or the initial value, whether it's initial as in the beginning of time initial, some nice round number, or just initial, that's a number that you know, so let's just start working from then. So just keep in mind that accumulation, the total accumulation, total value, like the elevation at the coast, doesn't have to be 0. Even if we're using like A equals 0, our function's initial values don't have to be 0. Like because especially if it's something like, oh, population of birds in 2000, probably wasn't 0, and if it was, unless they just kind of migrate into the area, it's not going to become more than 0. But this doesn't have to be 0 even if A is 0. No matter what this number is down here as our starting point, f of A could have any value. It's just up to the, what makes sense for the problem. So closed form accumulation functions. Sorry, that's just a repeat of what I just said. So let's say I have this f of x equals 3x squared minus x. Its rate of change function would be this. That's like day 2 of finding derivatives, right? So if f of x is this 3x squared minus x function, its rate of change function is 6x minus 1 as its function rule. So that should mean that if I write 6x minus 1 in this spot here, well, I should call it 6t minus 1 dt, and integrate from any a to x, that should be the same as this f of x minus f of a. So this right here, this 6t minus 1 dt, integrated from, or allowed to accumulate from 4 through x. Since I know what this 6x minus 1 is a rate of change function for, this should be something I can relatively easily find a nice closed form expression for. Even without doing it from scratch, I can just say, oh, well, this is r sub f, and so I want to know f of, according to this formula up here, f of x minus f of a, so f of x minus f of 4. Well, f of x minus f of 4, when I have function f of x written out, would be 3x squared minus x minus whatever I get when I plug in 4, which is 48 minus 4, 44. So this expression, 3x squared minus x minus 44, is a closed form representation, or means the same thing as this integral expression here. And we know that because, well, I know that this is the rate of change function for f of x, 3x squared minus x. Its derivative is, its rate of change function is 6x minus 1. So going the other way around, if I'm trying to figure out accumulation with this rate function, I know I can use this function f of x to help me do that. So what if I have f of x equals sine of 4x? Its rate of change function, its derivative would be 4 cosine of 4x, right? So I've got a little chain rule to do, but nothing too tricky. So if I had an integral expression involving 4 cosine of 4x, then I know that that's accumulation at this rate, this rate corresponds to this net accumulation or total accumulation. Could be either one, because sine of 4x at x equals 0 is 0. But this is an accumulation from, let's see, let's go from 0.1 through x. Well, this, allowing this rate for cosine of 4t dt, letting t vary from 0.1 through a general x, I know that it's going to accumulate in a pattern of the sine function. So all I have to do to find the net accumulation between 0.1 and x is f of x minus f of 0.1, which isn't something that I want to work out numbers for, but it would just be sine of 4x minus sine of 0.4, right? So take a look at these three. I've got a rate function 3x squared. I didn't write down what function g this could be the derivative of, but I bet you can figure out something that'll work just by doing a little bit of thinking backward. But think about the meaning and the value of, or expression for, I guess I should say, each of these three slightly different accumulation functions. And they are all functions. They're functions of x. They just aren't named. All right, so if I had a rate of change function, the rate of change of function g, according to this, r sub g of x is 3x squared. What does g of x have to have in it in order for this to be its rate of change function? X cubed, right? Now, just as a side note, it could have some other things in there too. It could be x cubed minus pi or x cubed plus 17 or lots of other things. But those constants don't affect the rate, so it also doesn't affect the accumulation. It's just that those would have different individual values. But these are all asking about accumulation between 2 points, so it doesn't matter these like particular constant terms that we could imagine. So we just have to think about what does g of x have to have in it. If it has this as its rate function, it has to have x cubed. It can't have any other x's because that would change the rate. It can't have any other like divide by something or take a square root of something that has x's in it because that would change the rate. So it has to have x cubed. It can't have anything else with x's in it. It could have other constants, but we don't care about those when we're measuring net accumulation. So let's just say g of x is x cubed then. That would mean this expression, which measures the accumulation or the net change in the y values of function g between x equals 1 and a general x. To find this, I'm going to do final minus initial. So g of x minus g of 1. So x cubed minus 1 cubed. This one, same rate, just different starting point, x cubed minus negative 2 cubed, so x cubed plus 8. And the last one, x cubed minus quantity pi plus 2 cubed. Let's just leave it like that. That looks a little unpleasant to multiply out and write any other way. So the meaning of each of those is what happens, the net change in the y values. So how much, I know x cubed is an increasing function. This tells us how much it increases between 1 and x. Now if x were something less than 1, that net change would come out to be something negative. It doesn't actually, although it makes more sense to write it 1 through x if x is larger, it doesn't have to be. It can be any valid, variable something. And with polynomials, anything that fits in the domain is absolutely everything. All real numbers are perfectly fine. Even imaginary numbers are fine. But these expressions here, they all represent accumulation, starting at different initial values, positives, negatives, irrationals, whatever, and going through a general x, which we can imagine to conceptualize this as being to the right of that starting x value, but in reality it doesn't have to be. So just to point out, this is just what I said earlier. If I know that g of x is x cubed, then its derivative would certainly be 3x squared. Its rate of change function would be something we could write as g prime of x, or r sub g of x equals 3x squared. But there are infinitely many things that have the exact same derivatives. In fact, g of x could be any one of those things that we had as an answer to the previous problems, x cubed minus or plus something else. Any of those could potentially have been just our original g of x function, and our problems would have worked out the same. It's the same sort of thing as if I say, well, if the equation of a line, let's see, a line has a slope of 7, figure out how much the y value increases from 1 to x. It's like, well, it has a slope of 7. I don't know what its y-intercept is, but if I go from 1 to x, I just need to know how far 1 is away from x and then multiply that by 7 because it's a constant rate of change. Or in other words, I just deal with the 7x part. I don't deal with the plus b part of the y equals mx plus b. So these constants at the end, these are the results from the previous problems, but they all could have actually been the original g of x function, whose derivative is this r sub g of x. And all of those questions on the same page would still come out exactly the same. So an indefinite integral is something we're going to be talking about a little bit more after your test. This isn't something like this, all these kind of getting into the details of how to get closed forms for all of these is something that you'll see more of on your final exam. But just as a, how do you deal with this? Generally what's done with this, just to tie up this, dealing with accumulation and the fact that we could have mystery constants that we don't know about. If I just want to generally describe the sort of thing, like what I asked, what does g of x have to have in it? We use symbols that don't have as much meaning to them, but they come from the accumulation we were just talking about. So something like this, 3x squared, and then an integral in the front of it, but not from any place to any place else, but just generally, if I'm accumulating at this rate, so this is kind of a generic expression, if I'm accumulating at this rate, then the original function must have been something of the form x cubed, and it could have had constants tagged on. So these sorts of statements, they're not solving specific problems. It's just kind of making, it's kind of like saying math rules. It's like if I have something that's accumulating at a rate 3x squared, then its function must have an x cubed, and it could have a constant. But that constant could be 0. This is the symbolic way to express that concept there. It's not solving a particular problem, but what it does say is that anything that accumulates with the same rate is a cubic polynomial, and you can think of this as being like, I don't know, I guess tangent line, like they'd be parallel cubic functions. They all like are just shifted up or down from one another. So they're all it's a family of functions that all have the same rate function, and they're all just differ by a constant, if there's anything. So just terminology-wise, I was saying whole sentences to express this, but this is generally how it's written in math. If I want to express the sorts of things that accumulate at this rate, 3x squared, we say this. I mean, the symbol for this is the generic integral sign with no numbers on it, just to mention accumulation, and then this plus c to indicate that there's an infinite number of possibilities, but they all just differ in this one potential way. The x cubed has to be there. There could be something else. So I'm going to stop at that for today. We're going to talk about some more properties of integrals and such after your test, but let's see. I think there's one other thing I wanted to mention test-wise. Net and total, fundamental theorem of calculus, open expressions. We hadn't talked about those in a while. Maybe not. I think I might have covered everything already. Let me just pull up here. Thinking about these, just as a challenge. So here are 4 examples of that kind of generic integral expression. So generic accumulation, the first one we just did. The second one should look familiar maybe from the rocket basketball, and then these are just random things I made up. But what I would like you to do just for a moment to kind of review derivative rules, some basics, and kind of a brief look forward as to what's coming up next. See if you can express in general what a function would have to have in it if these are how it accumulates. So it accumulates at a rate 3x squared, or accumulates at a rate t to the 1.3, and so forth. So think about what would need to be in the accumulation function in closed form. And I apologize, my writing thing is acting up, so I'm not going to be able to write on here. So the first 4 of these are power functions as the rate of change function. And for the most part, one power exception, power functions you're going to end up with from having taken a derivative or rate of change using power rule, which when you take a derivative, you decrease the power by 1, get a new coefficient. So this one we already went through. This is maybe kind of a setup problem. It's like, oh, well, this is exactly the derivative of x cubed, be 3x squared. T to the 1.3 power, it's a power function. If I took a derivative of something with a t to the 2.3 power, I'd end up with this, but it would have had the wrong coefficient. Any thoughts on what I might need to start with in order to end up with this with a coefficient of 1 as the rate of change function? I need a t to the 2.3 for sure. What coefficient could I use? 1 over 2.3. Not a very nice number. We could write that in a different form. But 1 over 2.3 as a coefficient. Ooh, sorry, I didn't mean to click on that. 1 over 2.3 as a coefficient in front of this, and I apologize, my writing thing's acting up. 1 over 2.3 in the front would cancel out the bring down the exponent and multiply it on effect of power rule. Same thing here, only it's got a coefficient already, it's just not quite the right one. In simplified form, what would I need to have in the antiderivative, the function whose derivative is this, in order to have 5w to the 9th as the derivative? What would I have to have? Yeah, w to the 10th, and what's the coefficient? Yeah, it should be, 1/2. All right, so if I have a 1/2 w to the 10th, take a derivative of it, that 10 and the half will turn into this 5 that we've got here. So similar sort of thing, messier numbers here. I'd need to have an m to the 12th for sure in the accumulation function associated with this rate. And so we'll play around with this, but just fussing around with the coefficients to make them come out right might lead you to understand this idea of, oh, just the reciprocal. When we're dealing with taking derivatives, we multiply it on a power. When we're undoing that or trying to work backward, we're going to divide by that power or multiply by the reciprocal of that power. So I'd end up with a negative 2 over 3 times 12. What does that reduce to? Negative 1/18 times m to the 12th should work out with its derivative to be this. Now, this last one is not a power function, but exponential function, right? And exponential functions, their derivatives are, their powers don't change, their exponents don't change. If it's e to the x, its derivative is e to the x. If it's e to the something else, I get to do chain rule. So we'll focus on some more things like this next time, but thinking about the same sort of concept of, oh, if I were taking the derivative of this, there'd be a times 4 that happens, but otherwise it'd look just the same. So if I'm working backwards, instead of multiplying by 4, I'm just going to divide by 4 instead. So kind of this backwards concept of chain rule. It's like, oh, divide by 4, so it's 5/4 e to the 4b. Would have to be in the derivative. There wouldn't be any other b's. There could be constants, but in any case, you don't have any additional assignments other than the quiz that you need to complete before your test on Thursday. Take a look over your old assignments, specifically if you still have questions related to the optimization-related rates question or implicit differentiation. Those are our 3 most recent topics. Please make sure you go to office hours, tutoring center, email, talk to somebody, figure it out, because I don't want this to be a mystery going into Thursday's test. So, test Thursday, make sure you bring a pencil. It is Scantron, and I will get here as early as I can and check your ID at the door and get you a Scantron so you can start bubbling away. All right, I will see you then. Yes. Oh yeah, you can bring a calculator. Sorry, yes. Not a cell phone, but whatever you want. As long as it can do like square roots, you're good. Yeah, that's fine. Yeah, you don't need graphing anything. It's just for computations. Oh yeah.